In the previous lecture on canonical transformation, we have seen actually the condition for a transformation to be canonical, and we have also discussed the generating function, that is the function which generates canonical transformation. And you have seen actually there are four forms of generating functions, and by a simple technique we have discussed how we can find the uh, different coordinates when the generating function is known. Now actually the results which I have discussed in the previous lecture directly by a technique, in this lecture I am going to deduce those relations. Actually in some of the examinations, particularly in university examination, this deduction is also important, although in competitive examination, as I have told you, this deduction is not important, but it's like a formula. You have to remember these things and you have solved the numerical problems. But as my lecture is for both type of examinations, that is the university examination and competitive examinations, so here first of all I would like to deduce those formulas, and after that we will see the important numerical problems so that you can solve the problems in your competitive examinations. So first of all I have mentioned here some of the results which we have discussed in the earlier lecture. You have seen that actually there are four forms of generating functions f, and the first form of the generating function I have told you that this is f1 equal to f1 of a small qk, capital Qk and t. It means the first generating function is a function of the position coordinate of old coordinate system, position coordinate of the new coordinate system. Here this capital Qk, you know, this is position coordinates of the new coordinate system and time. And after that we have actually seen in the heading of condition for canonical transformation a very important equation containing the generating function, and that equation is actually known as the general form of Hamilton's equation of motion. And what was that equation? You have seen in the previous lecture that this equation is like this: summation over k pk qk dot minus h minus summation over k pk qk dot minus h prime plus df1 by dt. You know here actually this h prime is what? This is the Hamiltonian of our system in the new coordinate system, and f1 is our generating function of the first form. And I have told you by a simple technique that how you can find the conjugate coordinates. It means if f1 is a function of a small qk and capital Qk, then it is possible to find the conjugate momentum small pk and the conjugate momentum capital Pk. If f1 is a function of a small qk, it is possible to find a small pk, and if it is a function of capital Qk, it is possible to find capital Pk. But how? I have mentioned this formula earlier in the previous lecture, but I have mentioned it by a simple technique, and I have suggested you to remember these formulas. Actually, in this lecture, I am going to derive these two important formulas, that is pk equal to del f1 by del qk, and capital Pk is equal to minus del f1 by del capital Qk. And this Hamiltonian, that is h prime, which is the Hamiltonian of new coordinate system, is equal to h, which is Hamiltonian of old coordinate system, plus del f1 by del t. So in this lecture our aim is to establish these relations. So you can see as the first form of generating function, which we denote by the symbol f1, is a function of a small qk, capital Qk and t. So from this relation, it is possible to find this time derivative of the generating function f1, that is df1 by dt. So simply you have to evaluate df1 by dt, and after that we will substitute that value of df1 by dt in this equation 1, and then you will see that these relations which I have mentioned here will be directly proved. So let us start to establish these relations. So as you can see, the generating function f in the first form is denoted by the symbol f1, and this f1 is actually a function of a small qk, capital Qk and t. Now in fact you know this k is actually equal to 1, 2, 3 and so on up to n, where n is actually the degree of freedom. So you can say that this f1 is actually a function of 2n plus 1 independent variables. Why 2n plus 1? Because the number of qk will be n, that is a small qk, and the number of capital Qk will be also n. So there are total 2n values of a small qk and capital Qk, and one value for time t. So actually there are as a whole 2n plus 1 independent variables. So definitely, since f1 is a function of 2n plus 1 independent variables, so if you want to find its ordinary time derivative, then definitely you should follow the rule of partial differentiation, and you know it. So let us try to find df1 by dt. Therefore, df1 by dt, what will be this? You can see, first of all, we will differentiate f1 with respect to qk, but you know k runs from 1 to n, so you must put the sign of summation here. So this will be equal to summation over k del f1 by del qk. And can you say what will be the product of it? This will be dqk by dt, because finally we have to differentiate with respect to t, and plus now the second term will be summation over k del f1 by del capital Qk and d capital Qk by dt. And since t has only one value, so there will be no sign of summation here, so you can write this is del f1 by del t times dt dt. So you can see now it here. This is in fact summation over k del f1 by del qk, and you know dqk by dt. This will be written in the dot symbol as qk dot, and plus del f1 by del capital Qk, and again this dqk by dt, this will be written as qk dot, and plus del f1 by del t, because you know this dt will be equal to 1, so this will be simply del f1 by del t. Now say this is your equation 2. Now we will simply substitute this value of df1 by dt in our equation 1. You can see here there is df1 by dt. So let us substitute the value of df1 by dt which you have just obtained. So substituting this value in 1. So from 1 and 2, what will be your result? You can see this is your equation 1. So this first terms inside the first bracket will remain at is. So you can write this is summation over k pk qk dot minus h and minus, again see this equation, summation over k pk qk dot minus h prime, this will also remain at is. So this is summation over k capital pk capital qk dot minus h prime and again you can see the next term is what? The next term is df1 by dt, and as I have told you that we have to substitute the value of this df1 by dt from this equation number 2. So let us put it. So this is plus summation over k del f1 by del small qk dot and plus del f1 by del capital qk dot and plus, see here, plus del f1 by del t, and this is equal to 0, since in RHS of this equation 1 you can see there is 0, so that will be equal to 0. Now let us write this equation again, but after some rearrangement. You can see, since in this term you can see here there is qk dot, and in this term too qk dot is present. So associate these two terms by taking this qk dot as a common factor. So let us take it like that. So you can write summation over k, see here, summation over k pk, and when you will associate this, see here, since here is minus sign, so this term will become minus. So there will be minus del f1 by del qk minus del f1 by del qk, and qk dot is as a common factor. Again you can see in this equation, in this term capital qk dot is present here, and in this term too capital qk dot is present. So we can associate these two terms again, taking this capital qk dot as a common factor. So, and since here is minus sign, so I have taken here minus, and this will be what? This is summation over k capital pk and plus, you can see there is plus sign here, del f1 by del capital qk, and capital qk dot is a common factor. So the terms which I have underlined has been taken. So what are the remaining terms? You can see here there is actually minus h which remains, and here is minus plus, that is plus h prime, and again this minus del F1 by del T. I am saying minus. Why minus? Because due to this minus sign, you can see here will be minus del F1 by del T. So you can write the remaining terms in this manner. This is plus H prime minus H minus del F1 by del T, and this equal to 0. Now see, as you know that this Qk and this capital Qk and capital Qk are actually the independent variables, and if this small qk and capital Qk are independent variables, then this Qk dot and this capital Qk dot will be also independent from one another. So in fact, in this condition, this identity will hold only when the coefficients of this small qk dot and the capital Qk dot will be separately 0. Only then this equation will hold. So you can say as Qk dot and this capital Qk dot are independent variables. So for the validity of the above equation, what we will do? We will take the coefficient of these quantities equal to 0 separately. So now you can equate Pk minus del F1 by del Qk equal to 0, because in first term you can see the coefficient of this Qk dot is this much. So this will be equal to 0. And so you can see here that this small pk is equal to del F1 by del Qk. Del F1 by del Qk. So you can see we have proved this result which I have mentioned in the previous lecture directly. And again you can see that the coefficient of this capital Qk dot is this much. So this will be also equal to 0 for the validity of this identity. So again you can write capital Pk plus del F1 by del capital Qk is equal to 0. And if it is 0, you can see this capital Pk will be what? This is simply minus del F1 by del Qk. Minus del F1 by del Qk. So you can see this result which I have mentioned it here is have been actually proved. Now equate the last term to be also 0, because if all these terms are separately 0, only then this 0 in RHS will hold. So we can also equate to 0 the last term. So in this condition you can see that H prime minus minus del F1 by del T, not plus. This is minus del F1 by del T. This will be equal to 0. And so you can see that this H prime is equal to H plus del F1 by del T. And say this is your equation 3. So you can see these results which I have mentioned in the previous lecture directly by using a simple technique. Actually in this lecture we have derived it or we have proved it. Now you can see when you will actually integrate this equation 3a, equation 3a, then equating this equation sorry so not solving this equation 3a, it is possible to find capital Qk, because this f1 depends on the capital Qk. So in fact by the process of integration, or simply you can say solving this equation 3a, it is possible to find Qk as a function of this small qk and a small pk. And similarly solving the equation 3b, it will be possible to find the value of capital Pk in terms of when once you get the value of this capital Qk, then from this equation it will be possible to find the value of capital Pk. So let us see. You can see it here. You can say solving equation 3a for capital Qk, it is found that, this is just a theory, so I am writing only the rule, but when we will see the proper problem, then you will see how such equations are solved. So when you will solve the equation 3a for this capital Qk, solution should be for capital Qk, then it is found that the value of capital Qk will be obtained after solving that equation, and that Qk will be obtained actually as a function of a small qk, a small pk and t. And you know this is just a canonical transformation, because in canonical transformation we actually transform the a small qk and a small pk in terms of capital Qk and capital Pk. So this is this will be the first transformation equation. Now once you know the value of this capital Qk, then we will simply substitute this value of capital Qk in this equation 3b. And after putting the value of capital Qk in this equation 3b, we will be able to find this capital Pk. So in this way capital Pk is obtained. We will see later on by the problem that these things, how these things are applied. It will be clear when you will solve the numerical problem. So you can say when equation 4 is used in equation, which equation? In this equation 3b. In equation 3b we get, then we actually get the value of the conjugate momenta capital Pk, and this capital Pk will be also obtained as a function of a small qk, a small pk and t. You can find it. So this is our starting equation. For the first form of generating function, you can write these two relations, and After writing these two relations, first of all we will solve this equation 3a for capital QK, and when we get the value of capital QK, the same value will be substituted in the equation B, 3b, and after that you will get actually the value of this capital PK as you can see it here. So these are actually the transformation equations or canonical transformation equations as you know. So you can say that equations 4 and 5 are the required transformation equations. So equations 4 and 5 are the required transformation equations. So in this way you can see how easily we can find the canonical transformations. If we are given the coordinates of the old coordinate system, that is small qk and small pk, it is possible to obtain the value of capital QK and capital PK, but by the use of these two equations. You can see it here. So for solving the problem based on this concept, we must remember it. And how we will remember it, I have mentioned the technique in the previous lecture. Now in the next lecture, we will see the second form of the transformation equation for the second form of from the second form of generating function. But before that, we will have to see a particular transformation which is called Legendre transformation. So in the next lecture, first of all we will discuss the Legendre transformation, and then we will obtain the transformation equation for the second form of generating function.